Hey, hey! All right, this is our last lecture for OChem 1. We're going to be doing Chapter 12, Section B. So, last time we talked about reduction, now we'll be talking about oxidation. So, in order to oxidize something, we're going to have to use what's called an oxidizing agent. And those agents fall into two categories. So we have something that either is going to have an OO bond or a metal oxygen bond. In other words, things that have oxygen to give off. It has to be able to give off an oxygen. So some examples would be O2, O3, ozone, H2O2, which is hydrogen peroxide. And in addition, there's these other three things. The main one that we'll run across is this MCPBA, and we'll see it a lot pretty much throughout this chapter. That's kind of the main go-to one. But again, any of these work, and when we come across O3, we'll see why it's decent. The peroxy acids themselves, these guys have their own category, and we'll find out why they react a certain way here in a little bit, and we'll find out what makes these a little more special. So we'll also be talking about hexavalent chromium. That's chromium with 6+. So maybe some examples of that might be like a Cr2O7K2, something like this. Or we're going to run into CrO3 is also kind of standard, or PCC. So anytime we see those two, or even this one, we'll know that it's an oxidizing agent. Last but not least, manganese. So we have permanganate, potassium permanganate, and this osmium tetroxide. So we'll run into osmium tetroxide and realize that it's a special condition as well, and silver oxide. So all of these are oxidizing agents. All of them have different strengths, different specificities, so things that they're going to be able to do and not do depending on which molecule we look at, just like all other reagents that we've talked about this semester. Okay, so some things you can do. You can take an alkene and you can oxidize it into an epoxide. You can oxidize it into a diol. You can oxidize it into a carbonyl compound. And I'm actually going to take the time right now to go through and tell you which reactant will do what thing, just so you have it all in one place. So for example, if you want to turn an alkene into epoxide, you're going to need a peroxy acid. So for example, the MCPBA we just talked about, or any peroxy acid from the previous page. If you want to take an alkene and turn it to a diol, it depends if you want it to become a trans or a cis diol. So if we want it to become trans, so one would be on a wedge and one would be at a dash, let's say. If you want it to become trans, you're going to want to use a peroxy acid and water. So first you'll be reacting it with a peroxy acid. Second, you'll follow it up with water. Like most alcohols, you usually end up with some kind of a negatively charged oxygen, and you're going to want to add water. All right, if you want it to become a cis diol, you're going to use KMNO4 permanganate, or this osmium tetroxide that we talked about. And you're also going to want to follow this up with water. Okay, so those for the diols. Then we have the carbonyl compounds. If you want to take an alkene and split it up, notice that there's an oxygen on either side. You've essentially just made two ketones out of an alkene. You're going to want to react it first with O3. And second, you can use a couple things. You can use CH3S, CH3, dimethyl sulfide, or you can use zinc hydroxide, which is, I'm trying to write a small ZnOH, and you got two of them. So both of those situations, first ozone, then one of those two things, we'll break it apart into a ketone like that. Then you can take an alkyne and break it into two carboxylic acids. So notice the alkene, we start with an alkene, and you can put 2 oxygens on it. We'll talk, there's some other little things you can do here and there, but for the most part, you just add 1 carbon-oxygen bond, or I guess this technically would be 2. Here, you're gonna add 3, 1, 2, and 3. So with an alkyne, you'll get the 2 carboxylic acids. The way to do that is with O3 and H2O. All right, and last but not least, we have alcohol, and you can turn alcohol into an aldehyde or ketone or carboxylic acid, depending on if it's primary or secondary. So if you have a primary alcohol, if you have a primary alcohol, I'm gonna write it up here, and you react it with PCC, you're gonna get an aldehyde. And I'll show you how that works. If you have a primary and you react it with potassium chromate and follow it up with, let's say, sulfuric acid and water, then you can get a carboxylic acid. So you've essentially really oxidized it twice to get to something like this, a carboxylic acid, if you have a primary alcohol. If you have a secondary alcohol and you react it with PCC, you'll end up with a ketone, much like the situation you just saw here, going to this. And you could also take a secondary alcohol and do the exact same thing you did here with K2, Cr2O7, potassium dichromate, along with sulfuric acid and some water. And you will also get a ketone. It doesn't matter, you're stuck with a ketone. Okay. All right, so hopefully this gives us a general idea of what we're gonna do today. We're gonna go through, of course, kind of like we do every lecture, each one of these and see what happens, break them down a little bit more. Okay, so let's begin with epoxides. So here we said you can take some kind of peroxy acid, an alkene with any kind of peroxy acid, and you can make an epoxide. And you sure can. Okay, so here you have an alkene, you react it with some kind of peroxy acid, and you end up with the epoxide here, same thing here. This is the MCPVA, in which case we get this. Also an epoxide. The way that works is a little bit funky, but kind of fun. So let's take a look at the mechanism. So let's say you have your peroxy acid, some kind of R, doesn't matter what it is, but you've got the peroxy portion of it. And what the peroxy portion of it is this oxygen bound to another oxygen like this. So this is the peroxy portion, and it would have an H on it like there to keep it stable. Okay, so if we take this thing, this peroxy acid, and which is what this would be called, this section right here is a peroxy acid, and we go ahead and react it with an alkene. So let's say carbon, double bond it to another carbon, who cares what's on it, I don't. What's going to happen is a lot of stuff is going to happen. This electron is going to bond with that electron. This electron is going to bond with that electron. So now you have a new bond there and there. So essentially you've just created the epoxide. So the last oxygen on this peroxy acid is the one that's going to be forming the epoxide. While this is occurring, and it all happens simultaneously, this oxygen, not the oxygen double lone pair that we're used to, but the actual bond of the oxygen over here is like, sup hydrogen, and grabs it. Then hydrogen's electrons are like, oh cool, I can come down here. And then the electrons over here, because this oxygen right here is disappearing onto this. These right here don't go onto this oxygen to become a negatively charged oxygen. Oh no, they go to fill the void that you've created here by taking this double bond and moving it over there. Now you have a cation, right? So these electrons are going to go here, making everything all better. And what you end up with is the carbon-carbon. And we still have those two things on it. But now it's bound to this oxygen here, like that. So you've got your epoxide. And then what's left of this will be this, this thing now has the hydrogen on it, right? And this is now a double bond. So you end up with R, double bonded to an O, like this. And then this oxygen, which was here, is now bound to an H. Hooray! Okay. And that is the mechanism for creating the epoxide out of an alkene via oxidation. Okay, so a cis alkene gives an epoxide with cis substituents. A trans alkene gives an epoxide with trans substituents. So let's talk about what that looks like. If you have, for example, a cis alkene, like this, and you react it with MCPBA, you are going to get an epoxide. Remember the carbon here, or this carbon and this carbon here, they grab onto the oxygen. And in one case, you'll have the methyl groups will be like that. And in the other case, you'll have methyl groups like that. Okay. Okay, so here we had cis, and you end up with a cis situation. Now let's take a trans butene like this, also reacted with CPBA, and we already have an idea of what's going to happen, I think. The epoxide joins there, and you'll have one cis, one trans, and of course it's an enantiomer here. There. Okay. All right, so hopefully that goes through epoxides decently. So yeah, pretty much that's all we need to know about epoxides. The mechanism is a decent thing to have a general idea of what happens. But mainly if you have a cis, you're going to end up with a cis epoxide. If you have trans, you're going to end up with a trans epoxide. All right, moving on to dihydroxylation. It's going to come in two types, anti and syn. So dihydroxylation is just another name for adding two alcohols. So you are going to add two alcohols here. And you're always going to start with an alkene. So on our first page, we talked about how you're going to do that with a peroxy acid. So any kind of peroxy acid and then water will form a dihydroxy acid, but it will form it via the trans. So again, you can get anti or you can get syn. If you have anti, that's when you're going to get trans. If you have syn, that's where you're going to get the cis addition. All right, let's do some examples and make sure we're okay with that. So this peroxy acid, in this particular case, is going to make an epoxide. So the way by which this occurs is this makes the epoxide, because we already know that this thing makes an epoxide, right? So your intermediate would be that. And then you followed it up with H2O. And we already know this is going to grab the AH, and then the OH comes in and attacks it and follows it, and this thing goes up there. And we've talked about this reaction many, many times. So this would be the first step. And then step 2 is why you get this. And again, the water can come in and attack here, or the water can come in the front. So it can do backside or front side attack, and that's why you end up with a trans diol. In case that wasn't clear enough, I probably didn't even need to draw it. There's a picture of it right here. So again, you got the alkene, you react it with your peroxy acid, and you end up in this situation. Then you can have OH minus coming from here or OH minus coming from there. Doesn't matter, and that's why you're going to get the enantiomers or the trans product. All right, then we have the syn dihydroxylation. So instead of having a peroxy acid, this is where you use that manganese 7 or the osmium tetroxide, right? We'll talk about it here in a little bit. This tends to be really cheap and used a lot, but you can't be as selective with how it works. And therefore this tends to be the more common when you really need good control of your diol and where you're adding it. But either one will end up giving you the same product, and it's via syn hydration. It's via syn addition. In other words, we get the cis product. Now, this adds very similar to, well, actually, let me see. I think I might show you. Yeah, I do. Good. Very similar almost to the peroxy acids, and that you end up creating a bond with oxygens out of either one of these. And you can see that this manganese complex is now attached to the double bond. And now essentially you've added the oxygens. Then you follow it up with water. Essentially these guys are going to grab the H's. It doesn't go through it, so we don't need the full mechanism. These guys are going to grab the H's, and that's going to allow this manganese complex to take off and hit the road. Again, these are two different methods. This is just the cheaper one, and this is the more expensive. This is also more selective, and that's why this is used in really important reactions. Okay. Oftentimes when you're doing this, it can be really expensive. And I don't know why I added this. This is just like a side note, and really I don't care if you know it or not. But if you come across NMO, it's added to make this osmium right here a catalyst. So if you add NMO, which is this thing right here, it essentially makes the osmium 6 a catalyst, which allows it to kind of come back and be a product and then continue to go on. So you're not using very much because, again, the osmium is very expensive. Okay, so again, this is not really, I don't care if you know that or not. I'm kind of just don't like that I even wrote it on there. Let's go. Let's go. Okay, so again, you make trans products when you do a peroxy acid and follow it up with water. I didn't do an example of this because I felt rather comfortable doing this because it's very similar to stuff we've already been doing. But the syn addition again would work with either of these two things. The current example we've asked is what happens when you take the alkenes that it gives us, and has us do this. Okay. So with the sodium, and this would be called sodium bisulfate, by the way, in case we run into it. Okay, so let's draw the products when cis and trans butene are reacted with this osmium tetroxide. What's going to happen? So if we have a carbon, double bond it to another carbon. Let me get rid of this pen, it's dying. And so I'll add the H here and here. Okay. This is butene. Okay, I drew the carbons here and here to make it a little easier to follow. And we're going to react them first with 1 osmium tetroxide, and 2, we'll follow it up with NaHSO3 and water. Okay, so we said when it's cis, it'll be cis. And that was pretty much all we talked about. When it's when you want to get a trans product, use the other anti-addition peroxy acid method we talked about. But now it's saying you got cis and trans, so what's going to happen? Well, let's see. This will kind of put everything into perspective, I think. So we're going to add, remember, a diol, and in this case, the alcohol will add cis, because again, it started cis. This will be our H. This will be our methyl group. This will be our H. And this will be our methyl group. Now, if you got an enantiomer, for example, the methyl group and the H flipped around, it would still be the exact same thing because this is a meso product. So, for example, that. These are identical. So this I didn't think was too crazy. You're adding oxygen, everything kind of goes cis the way you would plan it to do. But what happens when you have a trans? Like this. Butene. So we'll react it with the same thing. First osmium, hydroxide. Second this sodium bisulfite. Sulfite. Did I write 8? Sulfite. And water. Okay, so in this situation, the alcohol, because again, this is always going to form cis, right? Both of these will form cis diols. Form cis diols. The only way to get this to form a cis diol is you're going to have to twist this one down, if that makes sense. So this will end up being twisted down. And so your final product, because you want the two alcohols to be kind of pointed in the same direction, at least I do when I go to draw it. So you're going to get two products. Both of them will start out like this, if that makes sense. So both of them are like that. We're good with that. But now let's look at the methyl groups. You started off with trans, so your methyl groups are going to be the trans things in this situation. So maybe one will be on a dash and one will be on a wedge here. In which case your hydrogen would be on a wedge and your hydrogen would be on a dash over here. And you'll have the exact opposite over here. In fact, it might even be easier to draw it with those alcohols down and just repeat the same thing up. In fact, that's what I'm going to go do. I'm going to take carbon, carbon, alcohol down, alcohol down. It's a little bit easier to see, and then you can keep, for example, you can keep the H on the wedge or the dash and the methyl group on the wedge, and you can over here, you're gonna want the hydrogen on the wedge like it was and the methyl group there, but because it's flipped up, it gives you a different configuration. So you can figure out R and S of these and you'll find that they slipped and flipped, and these would be enantiomers. Okay. So again, this kind of comes out not so bad because you're like, all right, I'm taking a cis thing and turning it into another cis thing. And there's no enantiomers because this happened to be a meso product. But again, everything that was on one side stays on one side. Over here, now we flipped it up because it started up kind of crooked, up and down. We're going to end up with one methyl group that's up, for example, and one methyl group that's down. All right, I wanted to go through it because it's not as intuitive as you might think. Okay, now we are on to cleavage of alkenes. Sweet. Okay, so not a lot to write here. I have a lot of pictures, but essentially anytime you have an alkene and you react it with an oxidizing agent, and we'll talk about specifically what it is. In fact, you can see down here, we're talking about O3. And then you can follow it up with we had zinc hydroxide or zinc and water and the dimethyl sulfide. So either of those situations will work at breaking things up. It's called ozonolysis. So ozone, you're taking ozone. Olysis, you're breaking. Lysis means to break. So we've cut these things in half. Okay, so you just cut them in half and put an oxygen on either end of the double bond. And it is that simple. So we just cut this thing in half. We redrew it, and then we put an oxygen on one end, and then we put the oxygen on the other hand. Okay. anytime you have a primary thing getting cut, or a mono substituted side of the alkene bond, you're going to end up with the aldehyde. All right, same thing here. You can see we cut this. So you get this little aldehyde right here and a pretty ketone right there. Okay. It walks through how ozonolysis works. Okay, part of the double bond grabs the oxygen, forcing this one down, forcing this one out and up somewhere, and it grabs a hold of that, and it almost makes like an epoxide, but with 3 different oxygens. So after that situation, they ignore what happens, and they're just like, see, don't you like how this oxygen just showed up between this bond? As you can, I can kind of imagine it though, because the electrons are moving this way and the electrons are moving that way, and these carbons are really positively charged, looking for something to help them out. So I can see them kind of grabbing a hold of this oxygen, or vice versa, this oxygen grabbing a hold of those positive charges there and there, and forming this thing. And then you can use zinc and water, or again the dimethyl sulfide, and you can break these things apart. So there's really no step-by-step mechanism that's been shown here, other than the first step of creating this molozonide, which you never see. All right, so the fun part about it is I think these are really not too horrible to draw. So all you do, again, break them apart, redraw each part with an oxygen on it, wherever the double bond was. Okay. So not too shabby, right? Even if they're attached, that's okay. You're still breaking them apart. You're not going to detach them, per se. But you can still draw them like this. And count the carbons, 1, 2, 3, 4, 5. And then we had 5 there, so that should be good. You just kind of redraw it with the double bond broken and oxygen on either side. A meme I've been wanting to use all semester but didn't is these are called, what we're about to encounter are called dienes. So anytime you have 2 enes, or 2 double bonds inside a molecule, it's called a diene. So here would this limonene, which is really common smell used in like cleaning products. It's the lemon smell you get, probably lemon smell in certain pledges, etc. That's called limonene. Anyways, you can start by adding ozone, follow it up with this dimethyl sulfide, or you could use the zinc as well, and you're going to get, every time there's a double bond, you're going to add an oxygen to it. So even down here, we've got an oxygen to it. Over here, we've got an oxygen, and then we broke this thing apart because we're breaking it right here and here, right? So this one has an oxygen, and then we still had this little guy right here that broke off and had to become an aldehyde there. All right, so that's kind of fun, right? I think it's decent. That was alkenes. Alkenes are relatively straightforward. We just took the double bond and then made oxygen out of it, a ketone or aldehyde, depending on the situation. Okay, here we've got alkynes. You have an internal or a terminal, right? With the internal alkyne, you're going to end up with carboxylic acids. Crazy, right? In a terminal alkyne, you end up with a carboxylic acid on 1, and this poor carbon, which is all alone, ends up as CO2. Trippy, right? Okay, so in both of these situations, we have internal. So you can imagine just breaking them apart. Again, we're going to treat it with O3 and follow it up with water. So you can just kind of redraw carbon, carbon to another carbon. And then on this carbon, we're going to have that carboxylic acid. So this was the first part. The second part, 1, 2, 3. And then on the fourth one, we're going to have that carboxylic acid. Okay, so those would be your 2 products in this situation. And this one, same thing, if we're reacting it with ozone and water, you're going to end up with something like this. And then we're going to have that carbon right there. And that's going to be a carboxylic acid. If you flip it around, you would get the exact same thing. So really, we just have two of these things as your products. All right, we're moving on. Okay, so now we even know how to break things apart. If I were to go back real quick here, to the second page really, I want to walk through where we've been. So we took alkenes, we turned them into epoxides. We took alkenes, we turned them into diols. We took all alkenes, we broke them apart just now. Then we moved on to alkynes, breaking them apart. Last but not least, we're going to talk about alcohols and how you oxidize alcohols. Okay. So, it depends if it's a primary or a secondary alcohol. So for primary alcohols, if you take PCC, you can turn it into an aldehyde. And that's not too bad. So you get a regular primary alcohol, you turn it into aldehyde. If you want something harsher, or you want to really oxidize this thing, you can turn it into a carboxylic acid if you use potassium or sodium dichromate or chromium 6 oxide, or CrO3 would work in this situation, all in the presence of H2O and H2SO4. So you can get this using that, or you could use CrO3 here instead. I should have written it up there. And you can get the carboxylic acid. So this is only with primary alcohols. With secondary alcohols, if you react it with the strong oxidizing agent, like this dichromate and H2SO4 and water, so the same stuff we use for the primary, if you use it for the secondary, all it does is turn it into a ketone. Okay, it's not as fancy, so you can only turn this primary into the carboxylic acid here, primary and alkynes. All right, and here we have another secondary, PCC. We'll also turn it into essentially the ketone. So for secondary, you can use either thing, and you're just going to get the ketone. Not as fancy. For tertiary, there is no reaction. Hopefully that makes sense, because to oxidize something, you have to add another oxygen-carbon double bond, or an oxygen-carbon bond somewhere. And you couldn't fit another bond in here because this carbon already has 4. So there's no way to make this a ketone, for example, because then that would be 5, and one of these R groups would have to leave, and R groups are not good leaving groups. All right, let's go ahead and test this out and see if we understand. So here we have a primary, and we're reacting it with an alcohol. If you remember, that's going to make it a primary alcohol. We're reacting with PCC, and that's going to turn it into an aldehyde, if you remember. So I drew 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And on the fifth one, this oxygen is no longer going to be an alcohol. It's going to become an aldehyde, like this. You could draw the hydrogen if you want to. I'm not going to because I don't like to. All right, this is really good because it's really going to test whether you got this down or not. Here we have a secondary. Here we have a secondary. And here we have a primary. Okay. If you remember, primary with PCC will turn it into the aldehyde. Secondary will turn it into just a double ketone, a double bond oxygen, and this will also be a double bond oxygen. The only thing you could do differently here is if you turn this into a carboxylic acid using that sodium dichromate or potassium dichromate or the chromium 6 oxide. Okay, so let's draw it out. We've got this going to that, and this will now become a double bonded O. This thing is now becoming a double bond O, and even this one has now become double bonded O. Okay, so even this one became an aldehyde. Again, if you had reacted with something harsher, it would have become a carboxylic acid, and that would have been the difference between the two. But it shows that in this next one, where we take this thing and we react it with hexavalent chromium. So again, we have a primary, so we expect this to turn into a carboxylic acid, and that's what it does. So that OH can stay the same. You're just going to add an O. There, so that's our carboxylic acid. All right, y'all. Woohoo! We made it! That is the end of this lecture. Hopefully all this makes sense that we started with. And if it didn't, well then memorize this at the very least, because this is what you're really going to need. And have a great week.